and simulation using at-risk and the DecisionTools suite. This is part 2 of a 3-part series, presented by Glenn Justice of Experience on Demand. My name is Jameson Romeo Hall, and I will be your host today, and I'll be available to help answer WebEx technical questions by chat. At this time, attendees are in a listen-only mode. Please note that as an attendee, you are part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by typing in the chat or Q&A panel. I would also encourage you to visit our website and sign up for a free trial download of our software, including our lead products, At-Risk, and the DecisionTools suite. We invite you to sit back and relax and enjoy today's presentation. And Glenn, you have control of the presentation.
Okay, thank you very much, Jameson, and welcome everyone. Good morning. It's about 10 a.m. St. Louis time for where I am. I'm sure we have a wide variety of folks on the phone, so welcome to everybody, and thank you for participating. Jameson, let me get this opened up properly here, and then we'll get going.
Looks good.
Okay. All right. Well, again, thanks very much, everybody. We have quite a bit of material to cover, so I'm going to get through the introductory slides fairly briskly, so we can get going. But before we do that, I just wanted to again say thank you to Palisade and Jameson for giving me the opportunity to do this webcast. I hope it's enjoyable and informative, and hope to do another one sometime soon. So
certainly, thank you too.
Yes, and this is the second of 3 webcasts, and we'll cover, as a quick recap shortly, what we did in webcast number 1, just to catch up people that aren't able to participate before. So my name is Glenn Justice. I'm a partner at a consulting firm in St. Louis called Experience on Demand. I've been in industry and consulting for roughly 29 years. My initial work in the industry was in the electric utility industry, where I served as a nuclear engineer, and over the course of time gravitated toward more finance and business topics. I went into consulting full-time in 2000 with a firm called R.W. Beck, again focused in the utility market space. And at that point, kind of gradually began working with more and more businesses outside of the utility industry. And currently, with Experience on Demand, work with really a wide variety of organizations, both small to very large. They can range from, again, utility companies to major industrials to retail entities, do some restaurant work, do some agriculture work. And I've really seen a lot of situations where applying advanced business analytics, and in particular, Monte Carlo simulation, can be very, very valuable. I'm going to, just for sake of time, I'm not going to go through the slide about Experience on Demand, but we welcome you to go to our website and learn more about our firm. We are St. Louis-based. We're a small firm of around 12 people, and I've really enjoyed working with these guys. So, but again, feel free to go to our website. You can learn more about Experience on Demand. In terms of our agenda for today, first I want to do a quick recap from the first webcast, again, just to catch people up that weren't able to attend the first webcast. But then we'll quickly transition into the learning objectives and the actual content for this webcast number 2. In particular, we're going to focus more specifically on the mechanics of applying at-risk to a deterministic model. We'll cover what-if analysis and how doing that within a Monte Carlo environment is different, and in important ways different than doing it from a deterministic model. We'll talk also about optimization and the treatment of discrete risks using triangular distributions. In webcast number 1, we really provided a 10,000-foot overview of advanced analytics. These icons kind of represent some of the prior slides we had from webcast number 1, but the key point we made was that Monte Carlo simulation, using tools such as DecisionTools suite, really provides not just more information in terms of the potential outcome or the potential results of a business, but more importantly, actually better and more dependable information in terms of more accurate estimates of the expected value of the business. We also touched on why companies such as Ernst & Young and others are investing significant dollars in advanced business analytics and creating things like centers of excellence for business analytics globally. We talked a little bit about the different forms of analytics. In particular, we mentioned the 4 that you can think of in terms of diagnostic or descriptive, historical analysis-based analytics, predictive analytics, risk management-focused analytics, and optimization analytics. We then produced a sample model, which was a hypothetical widget factory, and we ran the analysis both deterministically and with the Monte Carlo simulation to demonstrate that not only do you, of course, get the expanded information in terms of the potential upper and lower bounds of performance of the business, the mean value is significantly different from the deterministic value. The key driver of this behavior, we introduced the mathematical law known as Jensen's inequality, and we covered how that is really the fundamental reason why the simulation results will tend to differ from the deterministic results. And of course, that's driven by the fact that most businesses contain nonlinearities of various types as well as correlations. We covered the different components of DecisionTools suite in terms of the different things that each module does. And then we wrapped up with a high-level view of when you step away from the analytics, what does it really mean to engage in a successful business initiative, ranging from the importance of a good strategy well executed on through the notion of continuous improvement opportunities that or the notion of continuous improvement, that you need to focus on to continually advance your business. Some of the key conclusions we had, just to recap these from webcast 1 and then we'll move ahead, is that business modeling using Monte Carlo techniques can, at a minimum, provide valuable additional information about the expected and potential performance of the business. This information can lead to new insights and better, faster decisions. In many cases, these techniques will produce higher quality and hence more dependable information. Businesses that tend to benefit from simulation modeling tend to have one or more of the following characteristics. They have some degree of flexibility or optionality. They have operational or financial characteristics that are nonlinear or asymmetric. And they have business drivers that tend to be either positively or negatively correlated. And it turns out that most businesses have these characteristics to some degree. So in the second webcast, what we want to do is roll up our sleeves a little bit more and establish an introductory understanding of the actual mechanics of applying at-risk to a basic deterministic model, including some tips and tricks that I find to be useful. Understanding the differences and how Monte Carlo analysis fits in with sensitivity analysis, scenario analysis, and stress testing. We'll also cover the differences in applying Evolver versus Risk Optimizer for optimization. And then we'll spend a little bit of time talking about the application of triangular distributions as you think about project risk or the risk and uncertainty of the capital cost of, for example, in this case, actually constructing the hypothetical widget factory in our example. So in terms of applying at risk, the basic steps that I want to cover are, number 1, just specifying outputs that are of interest, identifying key drivers. We'll do that with top rank, another DecisionTools suite component. Specifying distributions, linking those distribution inputs to spreadsheet cells, which provides greater flexibility. Incorporating a correlation matrix, running the model, and then exploring the results. And to do this, we're going to go back to our widget business model that we covered in webcast number 1. Some of the additions we made to this model include the following. We've transposed the columns and rows to make it easier, model easier to use. Before we had time down in rows, and we had different outputs along the columns, and we flipped that around so we have our different key outputs in the rows, and then the time buckets in columns. It just makes it a little bit easier to manage the model. We've added the capital cost of the plant. We've expanded and made more detail the labor cost components. We've added flexibility to make the widgets or buy them at wholesale. We've added hiring and layoff costs of new manufacturing staff. We've added a safety stock requirement, and then we've also adjusted just the values in general to make the model behave in a more realistic fashion to make the examples work well. And what we have now is the new deterministic total net cash flow from the business. This is excluding the capital cost. It's $15.4 million, and what we had before was $11.9 million. So again, we've just made some adjustments to the model, and we now have a new deterministic value that we're going to be starting from. So what I'm going to do is open up the Excel model, and then we'll go through the mechanics of adding in some distributions. Jameson, can you see this at this point?
Looks good.
Okay. So what I'm going to do here, I just changed my plant cost back to 0 to demonstrate I'm back at this deterministic value I mentioned before. I'll highlight the other inputs that I just mentioned that we've modified. So we've included a plant cost of $12 million. Including the plant cost, we now have a new deterministic net present value of the business of $4.3 million. Again, the model we had in Webcast 1 did not include the capital costs of the plant. Here's where we've added some additional information in terms of hiring costs, layoff costs. We've looked at the fact that you're going to have a certain number of workers required to manufacture the widgets based on 20 man-hours required for each widget that's produced. Here's where we specified starting stock. This is, it's the safety stock requirement for the manufacturing business. We've also assumed that we initially have 0 starting staff, and we'll cover this more in depth when we talk about optimization, because this is the input we've chosen to optimize against when we get into that section of the model. So going back to the list of the basic steps mechanically of applying at risk, first what I want to do is specify key output. And really, in most of these cases, the key output is going to be a net present value or something of that type. So simply in this case, the net present value parameter we care about is in cell D1. And you'll see me refer to this shortly when we apply at risk. But first, what I want to do is identify the key drivers of the business by applying top rank. So top rank is another module of DecisionTools suite, and it does automated what-if analysis to a deterministic model to help explore what are the key drivers of the model. So I'm going to jump over here. I'm going to launch top rank in my model. Okay, first what we do is we're going to basically add, pardon me a moment here. What we're going to do is just jump over to the analysis settings. And what we're going to do is we're going to basically do plus or minus 10% changes in terms of the key inputs that we identify. What happens is the model automatically identifies those inputs. Now, and typically in a lot of models, what you will have are many combinations of inputs and outputs and intermediate calculations. So what I find to be useful is to also define the range of cells in which we allow the model to search for inputs. So what I've done here, as I said, we're gonna do what if analysis when the model starts. We're going to search for the inputs, but then I'm going to set some ranges here. And in this case, what I've done is I specified this particular column of inputs for the model in terms of looking for key drivers of the business. So you can see it highlights here the search range I'm going to use. I'm also going to specify the key output, which in this case is this cell, D1. And actually, I'm just going to rename that net present value. And now what I'm going to do is run the what-if analysis. Now again, keep in mind that this what-if analysis is being executed within a deterministic model, and this has bearing later on when we talk about the differences between doing what-if analysis in a deterministic versus a simulation-based model. So it's setting up the problem. We've got 19 inputs to vary. It's going to do 95 different calculations, and we're going to run it. And what we get is this nice tornado graph of the net present value. And so the biggest single driver of the results of the deterministic model are the price of the widgets. We then have the amount of material X, the price of material X, the amount of material Y, and the price of material Y, labor time per unit, pay rate, retail market plant cost, and so forth. So those are the key inputs for the model that drive the results. So what I'm going to do now is I'm going to just use the utility function here, which is a nice feature that are in all of the modules for DecisionTools Suite. I'm going to unload the top rank add-in. I'm going to close this set of outputs that top rank produced. Now what I'm going to do is go ahead and load in at risk. Okay, we now have at risk. We have the menu bar activated. So what I've decided to do, just by way of using this example, I'm going to select a subset of those key inputs to vary in at risk using selected distributions. And what I'm going to start with, first of all, is these variable quantities necessary to produce the widgets. And so what I'm going to do first is select this 20 pounds of material. So let's say I'm not really sure it takes 20 pounds. There's some distribution around that. What I'll first do is to choose define distributions. I'm going to choose, in this case, a normal distribution. And you can select from this very, very long list of possible distributions based on how you believe that input item behaves. But in this case, I'm going to choose normal. That's a commonly used distribution. I'm going to select that distribution. And the default parameters here are to use a mean value for the distribution that's the same as the deterministic value or the static value. It basically puts in a standard deviation that's 10% of the mean value. And then it also identifies a static value, which is the value that is utilized in the model when Monte Carlo analysis is not being run. And so you can see now we have this mean value of 20, which, since it's a normal distribution, is also the mode of the distribution, as well as these potential ranges. So I'm just going to click OK on this one. I'm going to do exactly the same thing on this next distribution. So I'm going to keep both of these with a 10% standard deviation around the inputs. Again, here we have a standard deviation of 1, which is 10% of 10. What I'm also going to do, just kind of hypothetically here, is I'm going to jump down and identify my layoff cost as being a variable. Now, what's interesting about this is that when you think about layoff cost for personnel, and one of the decisions relating to this business is how many starting staff do I begin to operate with, is that although on average you may have a layoff cost of around $500, let's say, to cover administrative costs of just processing people as they happen to be downsized from the business. Obviously, in this kind of situation, you can have other bad outcomes. So let's say in this scenario you lay somebody off, and it then involves some kind of legal action, or you end up having to go through additional steps to properly execute that layoff decision. What I've decided to do here is use a different form of distribution where the minimum is $500, but it can be much higher than that. So I'm going to choose the exponential distribution because I think that is a good representation of the behavior. It automatically populates with these results. But what I'm going to do is I'm going to really skew it here. And so as you can see here, the lowest value, let me blow this up here for you. The minimum value is 500, but you have these outlying values that become higher and higher and higher in the distribution. So I've determined that I think that is a good representation of my layoff cost. What I'm now going to do is do something similar with my prices. And in this case, what I'm going to also do is show you how to link cells in the spreadsheet to the actual specifications of the distribution so that it operates dynamically. What I'll first do here is pick the price of widget cell. I'm going to define my distribution. Now in this case, since I'm working with a price parameter, I'm going to assume that the prices behave in a log normal fashion. And that's because prices can go no lower than 0, but they can, in theory, go to infinity. And again, this is just a choice based on my observation of the behavior of the inputs. But I'll click the log normal distribution. And what I can do here now is instead of just using these flat values from, that at-risk takes from my spreadsheet, I'm going to specify these as being drawn from the actual spreadsheet itself dynamically. So here I'm going to select that same cell. Oh, just a moment here. Just a moment. Like that. And then I'm just going to copy down so that I have the same formula now for material A, referring to row D31. So I've now separately specified the mean and the standard deviation as a percent of each of these key inputs, and the same thing with material B. And so this has now introduced three distributions into my model. What I'm also going to do is copy that to the right. So what I'm now doing is saying I've got 3 independent distributions for each of these items. So I've gone from 3 now to 9. But I don't want to do all 12 of them just because that begins to make the model unwieldy. So what I'm going to do then is over here, starting with my 4th month, I'm going to simply refer back to that cell. And then copy that down. And then copy that over. And so what I have now is a total of 9 independent variables, which has quite a bit more in the way of degrees of freedom. But then I'm replicating that pattern for each basically quarter of the year. If you would choose to, you can basically create a separate distribution for every single variable there, but then of course the model becomes larger and larger and the performance will begin to deteriorate. And you get to the point of diminishing returns where you really don't gain much additional new information by having all those separate variables. So what I've now done is I've specified probability distributions for these values here for my input quantities. I've specified that here using a risk exponential function for my layoff costs. And I've now specified distributions for my wholesale prices of my inputs, material A, material B, as well as the widget wholesale prices. And I've referred in these distribution functions to these inputs here. And you'll see where that comes into play a little bit later. Now, what I'm also going to do is let's assume that I believe these distributions are correlated. So right now, the default in at risk is that when you specify each individual distribution, those distributions are uncorrelated. So what I'm going to do here is select these inputs. I'm going to select my Define Correlations button. As you can see here, it grabbed basically and created a matrix of those cells. I'm going to select OK. It's going to ask me for a location for the matrix, and I'm just going to choose to put it right. I'll just put it right there. And as you can see, it's now added this probability distribution. Or excuse me, this correlation matrix, pardon me. What I'm not going to do is run the model. Look at my key NPV output. And we now have this nice distribution, which right now is fairly lumpy because we ran this with just 100 iterations. So what I'm going to do now is I'm going to clean that up a little bit. Let's specify 1,000 iterations, and we'll get a smoother distribution. So you can now see that nice distribution here. The mean of our simulated model, if you recall before, we had a deterministic mean of $4.3 million. The actual mean of the simulated model is 5.8 million, which is obviously a significant difference. What I'm now going to do is go back to my correlation matrix. Let's say I think all these variables are in fact correlated by a factor of 50%. That would be an example of a correlation between these different price inputs. So in this case, I've just gone to my correlation matrix. I'm just going to use Excel here to replace the values of 0 I have in here with values of 0.5. Place all. We've replaced 36 of those. And now what I'm going to do is rerun the model. Now, if this is what I now believe for the correlations of these key variables, I now have a mean of 4.9 million. And so in this case, with the values being correlated in this manner, it actually drives down the expected value of this particular business. I'm going to go back here and change these back. and then rerun. Oh, we've got a crash here, Jameson.
We still see we're good. We're good with the meeting part.
Okay. Okay, I'm going to have to relaunch at risk here. Folks, I think this issue is my actual computer, and the combination of that with the webcast is what's going on. This model worked flawlessly for the last 24 hours. So let me restart that.
It's as soon as we're on a webcast, it uses up a lot of resources that
that would have been,
yep.
Right. Okay, now we have at-risk open again. Now, unfortunately, we lost our distributions here, so I'm going to very rapidly go back and build these.
Again, though, the irony of the little bit of trouble is actually quite instructive for us on this side.
Well, that's good.
Yeah.
So I just did these materials here. Actually, I didn't want to have a distribution there, so I'm going to get rid of that one. Just put 20 back in that cell because that's not one of the ones I wanted to choose. I'm going back to my layoff costs again. We'll choose exponential. If you recall, I wanted to make that even more heavily skewed, so we update that value. We're going to go down here. Let me close out these or hide these columns just for convenience. We'll go back to our input prices here. I want to input my risk log normal function here. My mean is going to point to that. My mean is going to point to that cell. My standard deviation is going to be that times that. Yeah, we definitely have a performance issue here with my computer. So if I go back here, again, if you recall, I was also going to use my F4 command to basically make the column references static. Copy that down, copy that over. Going to make that equal to that. Going to copy those down. And then I'll copy these all across. Okay. And there we go. So I'm going to save this. I think that'll be a smart thing to do. And double check that I have all the materials. So I've got my input quantities as stochastic variables. I've got my layoff costs as stochastic, and I have my price as stochastic. I just showed everybody a moment ago the correlation behavior. I'm not going to do that again. But then I will rerun the simulation. It wasn't too bad. And we'll go to our I forgot to specify that as an output. There's one last thing I forgot to do. And add that as an output like we had before, NPV. Rerun it. And there we go. We're back to our mean of $5.8 million. Get rid of this comment here. Okay. So we just showed the updated distribution after the updated distribution of the net present value, and we now have this value. When I ran it the second time a moment ago, I had a value of about 5.9 million also, which is what I had in this slide. So that's good to see that that's consistent. What I now want to shift to, just for sake of time, and I do apologize again for some of the technical difficulties, is talk a little bit about sensitivity analysis. And this goes hand in hand with this concept of Monte Carlo simulation. From a broader risk management perspective, there are really three categories of what-if analysis. There's basic sensitivity analysis, which is understanding the behavior of the model with kind of random inputs. And in many cases, those inputs are altered by units of 1 or maybe flat values of variation by 10%, those kinds of things, so that you standardize the relative proportions of the changes between the different input variables. Scenario analysis is a little bit differently. In most of the settings I've been in, scenario analysis is really defined as understanding the results of the model under assumed combinations of conditions that reflect historical events. So, for example, you might say, what would the behavior of the model be if we had a repeat of the depression that started in, or excuse me, the recession that started in 2008? And you could then also postulate future scenarios. You could have scenario 1, 2, 3, 4 might reflect a booming economy, might reflect a recession. You could identify maybe a carbon-constrained future if you're looking at power plant emissions. But the point of a scenario analysis is that you're looking at some integrated set of conditions that represent a plausible scenario that has either happened in the past or could happen in the future. And then stress testing is the most severe. It's really to understand the results of the model under extreme hypothetical combinations of conditions. The question then becomes, though, how do these fit with Monte Carlo analysis, and are they redundant, and is one approach better than another? And you get some interesting results here. And what you will find that, as with your mean values or your expected values, the sensitivity results also will vary depending on if you do this deterministically or if you do this in a Monte Carlo simulation. And the results of the Monte Carlo simulation will tend to be more reliable. So let's go back to our widget model. Now, if I were to do a basic, let's say, deterministic sensitivity analysis, let's say I changed my input of $1,500 per widget. Let's say I changed that to $1,400. I get this negative $3 million up here. Let's say I change that to $1,600. I get this value of $12.3 million. Now that would be equivalent to basically just determining or doing a sensitivity analysis within the deterministic model, pardon me. But the question becomes, well, if I really believe the results of the Monte Carlo analysis, shouldn't I be really looking at the sensitivity of the mean of my net present value distribution given those changes in my inputs? And this is where this comes into play, where I've linked my price inputs down here over to these cells up here. So what I'm going to do now is I'm going to change this to the $1,600 value. You can see that carries through here. And then what I'm going to do is run my simulation. And in this case, I'm just going to run it using 100 iterations just to keep things a little bit faster. So now I have a mean value of 12.7 million as opposed to the 5.9 million. If I assume my starting point is $1,600 per unit. But let's see what happens if I drop that down to the 1,400. Again, in the deterministic model, we've got a minus 3.6 million. But if I run this, and as you can see, that 1,400 is propagating through these cells here. Let's run the model again. In this case, the mean of my distribution of net present value, when you assume a $1,400 per unit widget price, is actually $944,000, which is quite a bit different than the negative $3 million that we had before in the deterministic model. In this particular run, I had 0.9 million. So in summary, the net present values of the deterministic model were negative 3.6 million, positive 4.3 million, and positive 12.3 million when I run those different scenarios with $1,400, $1,500, and $1,600 prices, versus this range here if I run the change in the mean of the NPV in the simulation model. And again, the reason for this is because of the nonlinearities. And so you end up with this distinction in your sensitivity results. Because of the nonlinear behaviors in the model, you will have different sensitivities and hence different actual risk behavior in the model, and we believe that that is best represented using the Monte Carlo simulation approach in the model. And especially what you find interesting is that down here in these adverse cases where you have the $1,400 value, you get dramatically different results. Obviously, a possibility of losing $3.6 million is drastically different than an adverse profit of plus $900,000 in that adverse case. Okay. So the next item we want to talk about is optimization. So there's two different components in the DecisionTools suite. One is Evolver, the other is Risk Optimizer. And Evolver is used for deterministic models. Risk Optimizer is used within your Monte Carlo simulation. So what I'll do here quickly is revert back to my probabilistic model. I'm going to change this back to my $1,500. What I'm going to do in this case, I'm actually going to, hopefully we don't have technical difficulties here. I'm going to extract out my at-risk add-in. But before I do that, what I'm going to do is swap out the at-risk functions. And so this is a very, very handy feature of at-risk where it takes the at-risk inputs, pulls them out, and puts them in a separate tab down under the risk swapped functions. and it then deactivates at risk. So I'm back here at my $4.3 million. When we optimize, we're going to do it against this particular variable here, the starting staff of my manufacturing plant. What I'm going to do here then is I'm going to actually go to at risk. I'm going to save this. I'm going to load in Evolver. As you can see, Evolver is now loaded. When I use Evolver, what I first have to do is define the optimization model. So in this case, and I've already pre-populated this, what I care about most is cell D1, and I want to maximize my net present value. The variable I'm going to look at independently is my starting staff for the manufacturing plant, which is in cell D23. And I'm going to specify that within the range. So you have D23 right here. I'm going to specify a minimum allowed value of 0, a maximum allowed value of 1,000. I'm going to say here that the only possible values that I can utilize are integer values. Also check my model settings. I'm going to allow it to do 1,000 trials, which I think is going to be okay in this particular case. So let's run it. So the question becomes, given the fact that I have these potential layout costs, what is my optimal level of starting staff? So Evolver did it as it's supposed to. It started with a value of 1 in my first simulation. It then looked at all these different possibilities between 0 and 1,000, and it found that trial 17, using a starting staff value of 544, produced the optimal output. In this case, that result is $4.8 million, which improves me from my $4.3 million. What Evolver has also done is then left this 544 in that cell D23 for my starting staff parameter. Jamison, we're obviously getting close to the top of the hour. Can we go a few minutes long, or what's your...
Oh, sure. Sure, that's okay. Fine.
I didn't know if we automatically shut down or not.
Oh, no, hope not.
Very good, very good. Okay, so just remember this value, 544. What I'm going to do is change that back to 0 now as my starting point. What I'm also going to do now is I'm going to unload the Evolver add-in. I still have at-risk active. I'm going to now swap back in my at-risk functions, which really this is a very handy feature that I use actually fairly frequently, especially when you want to deliver your model to someone that doesn't currently have at-risk. Okay, so what Palisade has done, which is pretty nifty, is actually implemented Evolver within at-risk, and they now call it Risk Optimizer. And the whole notion here is that optimization within a stochastic model is different than optimization within a deterministic model. But I still have the same question. Given my stochastic model, what is my optimal level of starting staff for my plan? So I'm going to start here. I'm going to also do my model definition. Now what I'm going to do, I kind of learned it's also good to clear out some of the at-risk results and just get everything kind of reset. So I'm going to clear my at-risk data just in terms of my simulation results. What I'm going to do here is I'm just going to rerun my simulation just to make sure it's behaving properly. So here again, I got my mean in this case with 100 iterations is $5.8 million, which makes sense. That matches pretty closely with what I had before. Now I'm going to go over to Risk Optimizer. Similar to Evolver, you first have a model definition. which in this case what I've done is I've pointed again to cell D1. That's what I want to maximize. And then I've specified again cell D23, which is my starting staff, and I've allowed a minimum value of 0, a maximum value of 1,000, and only integer values within the optimization simulation. Click OK here. What I'm also going to do, though, is look at my settings. Now, in this case, for it to do this, it's going to run quite a few simulations embedded within the optimization. So what I'm going to do is limit this to 100 trials just to make the length of time reasonable for us. But when I run it, let's see what we get. You can see down here it's doing my risk optimizer progress box. And I'm moving toward my 100 trials. Now, in this case, when I run it this way, within Risk Optimizer, I get a best value of 500 starting positions as opposed to the 544, which is almost 10% different, which can be significant. I've also run the same model at times, just to let you guys know, where that value can be was as low as around 100 or 120 staff members to start with. And so the optimal results can be very sensitive to the simulation results. But the point is, it comes out significantly differently than in the deterministic model. And again, you can see here where Risk Optimizer has then put that 500 staff person value back in my simulation. So in this particular run I did, again, the deterministic value for the optimal solution was 544. The simulated value was 500, which I think is a material difference. Okay, so let's move on to one last component here that I'd like to talk about. And again, I do appreciate everyone's patience to allow me to go just a little bit long. What we haven't done, if you'll notice, is we have not covered the uncertainty around the actual construction cost of the widget plants. And so I've added an additional tab here to my model, and I'm going to change this back to 0 just because that's what I have in my base model. So let's assume that I have this set of costs for my plant, and I've got these different items, which are the different phases of constructing the plant. So I have design of the plant, engineering of the plant, we have various board approvals, construction of the plant, and I've just, for sake of convenience, assume that each of these steps costs $1 million on a most likely basis. That then yields my $12 million in terms of total cost. I have some hidden cells here just for expediency. Let me blow those open. Let me expand them. In most cases, when you're talking about the construction of a facility, as you think about the project to accomplish that, in many cases you're going to think about what is your most likely cost for each component of construction of the plant. But in reality, you'll have a lot of data, both either your own data or through your contractor, that has ranges. And you could also have what is kind of the lowest cost I've experienced historically, what is the highest cost we've experienced historically. So let's just assume here for each of these, we're going to say $900,000 for each of these for a low, and we're going to say $1.2 million for the high. Now think about this. If you have this range for each individual value, and even though each one has a individually most likely value of $1 million, the question becomes, well, Should I use 12 million in my simulation, or should it be a different value? In this case, what you find that's very convenient within at-risk is the use of the triangular distribution shape. And so I'm going to, again, go back to my defined distribution. I'm going to select triangular distribution. I'm going to specify that. Oops, bear with me a second. I'm going to specify that cell for the low value, that cell for my most likely value, this cell for my max value. Put those back into the formula. You can see these cell references here. I'm going to choose OK. The actual simulated value, which is returned dynamically in the formula from at-risk, is actually $1.033 million. I'm going to do that same thing for all these other components. And in reality, that simulated value really should be more in the order of $12.4 million. What I can also do is specify that as an additional output. What I'm then going to do is return to my widget business model, go to the very top of the model, and my plant cost, in this case, I'm going to refer over to this value here. So two things are happening here. Number one, I'm using a more realistic expected value for my plant cost because, again, under bad conditions, there's a higher penalty than under good conditions in terms of that favorable outcome. And so you end up having a slightly skewed distribution. And so first and foremost, it's important to recognize that when you have those types of asymmetric uncertainties, that your actual expected capital cost will be higher than the sum of your most likely costs for each individual component. Furthermore, I've now introduced this as a simulation parameter using the risk triangular distribution formula for each of these. And I can now incorporate that into my widget plan economic analysis. So I'm going to go back to this, I'm going to rerun it. I'm going to go back to my 1,000 iterations. My new mean value is 5.6 million, which is a little bit different than the 5.9 before. We have a little bit lower minimum, a little bit lower maximum. And then also, we've incorporated the simulated plant costs, which is ranging from a value of, in this case, roughly around 11.8 million up to around a max of $13 million, which gives me greater dependability of information, greater insight into the totality of my, my plant construction decision. So in terms of concluding thoughts, first of all, DecisionTools Suite is very powerful, yet I find it to be relatively easy to use, except for some of the technical difficulties that I had because I had the webcast going on simultaneously. There really are many thoughtful user interface-related features, and there are a variety of tips and tricks that exist and that are worth learning within the DecisionTools Suite product. In addition to providing more dependable expected values, Monte Carlo analysis can also produce more dependable what-if analysis. And as with expected values, the what-if values are also impacted by nonlinearities and correlations. In similar fashion, optimal values are also impacted by model nonlinearities and correlations. To reiterate what we had from webcast number 1, that businesses that tend to benefit from simulation modeling tend to have one or more of the following characteristics. They have a high degree of flexibility or optionality. They have operational or financial characteristics that are nonlinear or asymmetric. They have key drivers that are positively or negatively correlated. And in fact, most businesses have these characteristics to some degree. Very high. As a preview to our third webcast, that's September 18th, Thursday. I believe it's also scheduled for 10 a.m. Central United States time. For the third webcast, we'll have a case study from a real company. We'll demonstrate the integrated use of at-risk and precision tree. We'll also discuss issues and lessons learned in implementing advanced analytics, including Monte Carlo simulation, in both small and large company settings. I just wanted to expand from webcast number 1. 3 additional references that I feel very useful is this financial modeling text. Competitive strategy is the classic and what some people define as the definitive treatment on what competitive strategy means and how to analyze it. And then Against the Gods is really a fascinating, it's a fairly lengthy book, but what I think is a fascinating book that talks about the history of risk management, and that one's authored by Peter Bernstein. That's the end of the webcast. Again, I apologize for going what looks like about 10 minutes long. Again, Jameson, thanks very much to you and to Palisade. Well, I'd be, of course, happy to answer any questions that anybody has at this point.
Thank you very much, Glenn. Yeah, I think we have time for a couple questions. We could answer. Oh, we just have a question about your slides and your model. Are they available? Will they be available to the attendees?
And I think what we've done there, Jameson, similar to the first webcast, the video will be made available in terms of a post video of the actual webcast. If anybody would like to have the slides themselves, they're welcome to contact me at the below email address that you see on that slide. What I'll also do, Jameson, is I'll send you the slides so that you have them and can field any such inquiries.
Perfect. That sounds like a good deal. I think that was the only question. We can just wait a minute, see if another one comes in. But yes, that was very instructive on my side while I was watching it, because I picked up a couple of things that I didn't even know. So I know that it was a little frustrating, instructive, and
right.
But we really appreciate this.
Oh, absolutely. It's my pleasure to do it, and I look forward to the third webcast. I think what we'll do